Okay, so hello everybody. Welcome to the webinar series. This is our second talk. So in order to move ahead with our priority number one, which is to entrain members of the coastal ocean research communities into US CLIVAR to study interactions between large-scale and coastal-scale climate, and in particular to move forward on our US West Coast ecological forecasting priority. We've invited Samantha Siedlecki. She comes to us from the University of Connecticut. I first had contact with her in the fall of 2014 when she was going to be the co-chief scientist on the first leg of the very first US GO ship cruise, P16 North, in the West and North Pacific. I didn't actually meet her until the spring of 2015 when the two legs connected in a pub in Hawaii. Sam received her PhD from the University of Chicago in 2010, where she was working with David Archer. She also received a postdoc fellowship at JASAL in Seattle, and that was followed by several years as a research scientist, also in Seattle, where she worked on forecast systems for ocean acidification in the Northwest Pacific. She was also a Carverley Foundation Fellow, and she moved to UConn in 2017, where she is now as an assistant professor. She's a co-author of the NCA4 and the Soccer 2 reports that were released a couple of weeks ago. And she's here to talk to us about her work forecasting hypoxia in the California current system. So welcome, Samantha.
Thank you. Can you guys all hear me okay? Well, at least those of you who are unmuted.
Yes, I can hear you.
Yeah, great. Well, thank you so much for having me. I'm excited to be here to tell you a bit about that forecasting work that Allison was just talking about and sort of how it connects to larger scale climate variability that's driving the skill of our forecasts and also the variability of the ecosystems that are starting to rely on them on the West Coast. So this is not work I do by myself. I do this with a large group of collaborators, and so I just want to acknowledge some of the live ocean work, which is a forecast system that I'll talk about a little bit later on. Parker McCready is the lead scientist on that, and he's at University of Washington and heads up the coastal modeling group there. Ryan McCabe, Burke-Hills, they both contributed observations, as well as Ryan helps a lot with the model validation. And then Neil, Sarah, Kristen, and Barb were all involved in the initial formulation of the simulations that I'm going to show you today. JScope is another forecast system that I'll talk about that also includes a large group of collaborators, all listed here. Isaac Kaplan and I have been working very closely on this for a long time, and he really connects us best with the fisheries. Okay, so what does a forecasting system look like in the Pacific Northwest? What are we shooting for? And so here's kind of a cartoon idea of a forecasting toolbox that we're working on. So you can see this axis is time here in this cartoon. And so observations end at some point and you move forward. But the observations, there are real-time observations out there ported by the regional IUS networks. And so we can rely on those to provide early warning systems for key metrics like low oxygen events or exceedingly warm events as those are happening more and more often. Also there's bulletins that are released that rely on those real-time observation systems as well as those forecasts. Specifically, there's one for harmful algal blooms that's delivered that Live Ocean contributes to. And then as you kind of move forward in time, there's the time scale of weather, sort of days to weeks. We have these short-term forecast systems like Live Ocean, which is for Washington, Oregon shelves, and now includes forecasts for the inland waters of the Salish Sea. And the Pacific Northwest HAB Bulletin, which now includes information from Live Ocean. And then as you move into seasonal systems, we have this JScope system, which I'll talk about, and also an EcoCast West Coast-wide seasonal forecast system, which Mike Jaycox is leading up, and I'll show you the sort of conceptual diagrams of what that's going to look like, as that's a work that's largely in progress. When we have this kind of gap in time of like from the interannual to decadal projections, we don't really have a lot of information about that, and that's, I think, a hot topic of research, but not something that we currently have information for. And then kind of going forward in the century timescales, we have several scales of projections ranging from purely temperature focused to biogeochemical all the way up to this Atlantis and ecocast kind of end-to-end forecast projections of what the ecosystem is going to look like, which I'm not going to talk about today. And so these forecasts are, designed in large part to aid in fisheries management. And so here's and fisheries management, there's decisions that are being made on various timescales. And so what's important is to kind of connect with the specific needs of the stakeholders and those decisions that are being made on those particular timescales. And there's a group in Australia led by Alistair Hobday that's been leading the way on this in lots of ways, not just the development of these types of systems, but identifying protocols and pathways to work with stakeholders best. So the Pacific Northwest, it's one of our stakeholders that's really essential in feeling the stress of the recent changes going on there. Is of course the oyster industry, and so in 2005 there was now a fairly long time ago now, they reached out to the scientific community because of issues that were happening at the hatcheries, and ocean acidification was identified as one of the stresses that was causing the issues at the hatcheries. And so, what is ocean acidification? It's of course the long-term trend in carbon dioxide that's driven by fossil fuel emissions. The absorption of that CO2 by the ocean drives a downward trend in pH and an upward trend in the carbon dioxide from the uptake of that fossil fuel emitted CO2. So here you can see that as a long-term record from Mauna Loa in the atmosphere by this red curve, and then the green curve shows you the at nearby Station Aloha, the PCO2 that's being observed in the water, which is largely keeping up with the atmospheric rise in CO2, and then the corresponding decline in pH observed at that same site as long-term record. And so this decline in pH and change in the carbon chemistry is also responsible for changes in aragonite saturation state, which is this omega symbol here. And so when you see that value get below 1, in some of the figures I'll go on and show, it means that there's an energetic threshold that's been passed for organisms that secrete calcium carbonate minerals. And so when it's lower than 1, it becomes energetically unfavorable for these organisms to produce that mineral. So this, that's happening in the open ocean. It's also happening in coastal waters, but to a large degree, the coastal waters are that trend is either being amplified or dampened depending on where you are and sort of what the coastal processes, the local processes that are going on. And so that was detailed in this recent paper by Laurel et al. In Nature Communications from 2018, which was highlighting the uptake rate of carbon dioxide and how that was varying by region. And so along the California current system, there's been work about what's going on with aragonite saturation state and sort of evaluating not only the trends but also the spatial and temporal variability. And so one thing that's complicated about observing these coastal systems is that they experience a lot more variability than the open ocean, and the California current is no exception. So here you can see a map of that aragonite saturation horizon, the depth of it, in the water column, and this iconic figure from a paper by Field et al. In 2008. And so areas where the aragonite saturation state is near the surface are highlighted here in red. And so you can see there's a lot of spatial variability in sort of the extent and presence of the corrosive water along the coast. And from one mooring location, NH10 off the coast of Oregon, you can see that in this time series from a paper by Harris et al., the sort of temporal variability that's experienced, again highlighting that threshold of 1 here. You can see for different years that over this seasonal upwelling season that we get undersaturated water events, corrosive events happening in the modern ocean along this coast. So the region is also stressed by harmful algal blooms. So in 2015, we had an enormous Pseudo-nitzschia bloom, which resulted in the closing of the Dungeness crab fishery, which was a huge loss, economic loss. Also, razor clam, which is a fishery that the tribes and recreational fishermen also rely on, was also closed. And this event was largely attributed to the anomalously warm temperatures experienced by the marine heat wave or the blob, event of that happened that year. And so this, which was detailed in a paper led by Ryan McCabe et al. In 2016. So another, environmental stress going on in this ecosystem is, of course, oxygen. So this is an older paper now, but it's still, the results still ring true in that oxygen is on the decline in the open ocean, but of course in the California current system we're experiencing an increased events of hypoxic events, which with increased presence of really low oxygen water, which can result in the mass stranding of Dungeness crabs. So another impact on this important ecosystem. So the coastal ocean, I study the coastal ocean in part because it brings these global change issues, makes them locally relevant. And so one example of that is through ocean acidification and hypoxia. So I really think about how these global changes are transmitted to the coastal ocean, what processes can happen locally to amplify these global changes, how those processes influence that local the spatial and temporal variability of those stressful indices, and then think about how local managers can adapt to the, if there's any tools we can develop to help them to adapt to these changes going forward. So kind of just to give a little background on the system itself, the region I'm going to be focused on is highlighted here by this box, and that sits in the North Pacific. And so the North Pacific current, that return gyre circulation bifurcates, and some water moves north becomes the Alaska current, and then some of that water comes south and forms the California current, and that water influences the region. There's also a countercurrent, which is largely seasonal in the area. That's called the undercurrent. And that brings with it very different water coming from the equatorial Pacific with properties that are higher in nutrients and lower in oxygen and more corrosive. So the waters that are brought into the region are also impacted by the process of coastal upwelling, which as the winds blow from the north, water is displaced offshore and you get deeper water brought to the surface. And so that brings these high CO2, low pH, low aragonite saturation state, low oxygen water up to the surface. And it also drives the high productivity, which allows for all the fisheries to exist in the region. So this was highlighted in a very nice figure from Feely et al. In 2018, showing all of these different processes and how they act together to create a local amplification of these oxygen, pH, and potentially even temperature variability on the shelf. So to sort of look at this system, I'm going to use a high-resolution model that relies on the Cascadia model setup, which was detailed in the Giddings et al. Paper 2014. It's a ROM simulation that has 40 vertical levels. It's very high resolution, 1.5 kilometers. It includes rivers and tides. And when I talk about the hindcast briefly, it benefits from physical data assimilation at the boundaries and in the atmospheric forcing, plus relies on data for the rivers. But the forecast, depending on the time scale, but in general, they rely on forecasted boundary conditions for the ocean and the atmosphere, as well as the short-term forecast uses a river forecast, but the longer-term one uses a climatology. And then an ecosystem model that was adapted from Neobanis by Kristen Davis in 2014, and that I added oxygen and DIC and total alkalinity so that we can model the hypoxia and ocean acidification stresses. So here's just a model evaluation, so from a couple of moored observations in the region. And so what you can see here is this is 2014 here, this is 2015. The model is in pink and the observations are in black. And both of these time series are from the bottom on the Oregon coast. This data is courtesy of Burke-Hales. And it happens to be a pH time series. And so what you can see is that even over the winter, going into these summer months, and the model's doing a fairly good job at capturing the trends and the variability in the pH, especially at depth. We also look at oxygen variability, so from a similar nearby mooring on the Oregon shelf. Here you can see temperature, bottom temperature, and bottom oxygen for 2013 through 2017, and this repeated seasonal decline in oxygen is well captured by the model when we send it compared to the hindcast. So what can these models be used for? They can offer, how can they offer support for local decision makers? One is by forecasting, either providing early warning systems, forecasted habitat changes, something about, or trajectories of pollutants. We use them for attribution experiments to understand the role of local processes like input of local nutrients, and also for test beds to explore mitigation and adaptation strategies. I'm only going to talk about the forecast today. So we are working on this forecasting toolbox where we're extending the regional, going beyond what the regional observational networks can provide and providing future conditions with this combination of this short-term forecast on the timescale of weather and the seasonal forecast, which goes 6 to 9 months out. This is not something that is totally unique to our area. There are other areas that are also working on development of forecasts, including the Gulf of Maine, Chesapeake Bay. There's another one in Puget Sound. There's an East Coast-wide one and a West Coast-wide one in development. So Live Ocean is the daily forecast system that's funded by the State of Washington's Ocean Acidification Center. And you can find out more information about it at this website. It relies on an atmospheric forecast, an ocean forecast from HYCOM, USGS river forecast, and then tidal forcing as well, all brought together in this regional ocean modeling system setup. And you can find out more at the Coastal Modeling Group website, but currently they're forecasting HAB transport pathways, hypoxia, ocean acidification events, tsunami debris, and habitat changes in the region. So this is just one trajectory of the HAB transport pathways that's shown here in this movie, where they rely on particle trajectories. And when they, from regions that are known HAB generation sites, when those reach the shore, then that releases a warning. And that was work that was really, those transport pathways within the model simulation were evaluated in that Giddings et al. Paper, which ground truths the tool for use of that. So Live Ocean is on the NANOOS web portal. Our regional IUS portal, and you can check it out at any time and compare it using the comparator to regional assets. So here you can see comparisons with water temperature as well as a pH sensor that's within the Nakata mooring that's within Willapa Bay. And one thing we're working on there is the optimal window. So like one piece that's directed again at that stakeholder's needs. Burke-Hales published a paper in 2017 showing that not only aragonite saturation state being above a certain level, but also that the organisms, specifically oysters, rely on there being a combination of warm water as well as this aragonite saturation state being above a certain threshold. And so that combination is something that we can forecast as well. Okay, so in the interest of time, I'm going to skip over the movie. The next forecast system is a seasonal forecast system called JSCOPE. It's JASEO's Seasonal Coastal Ocean Prediction of the Ecosystem. We are also hosted on NANOOS' website, and there's a paper detailing the system that I led in 2016. So that forecast system relies on a climate forecast system, which is a NOAA product that is a global model that produces forecasts many times a day, 9 months into the future. And then we couple that with this regional ocean model, that's a ROMS model that I was just talking about. And then from there, there's several habitat models and indices that are either in prep or out. So Isaac Kaplan has been leading the sardine habitat, which you can see the forecast of on the website. We are also working on a hake habitat forecast, a juvenile crab forecast that Emily Norton's leading, and an adult crab, Dungeness crab forecast as well, which Isaac is leading. And so our website, we have January initialized and April initialized forecasts for many years. You can go and check out the performance of how they've done, and also the latest forecasts to see what conditions are projected to be over the next 9 months. We do several indicators that you can see here, like chlorophyll, surface temperature, sardines, oxygen, saturation state, and other California current relevant indicators that have all been previously identified by the California Current Integrated Ecosystem Assessment. So in our paper in 2016, what we found was that doing experiments with some past forecasts or reforecasts, the system did have significant scale on the time scale of the seasonal forecast. So that's indicated here by the spatial correlations between the anomalies from the forecast and the anomalies of the hindcast fields. And one interesting thing to note was that in doing the skill assessment, what we found was that the bottom temperature and bottom oxygen, so the sort of benthic habitat, had more skill than the surface fields. And so what that did was it kind of drove us in our next phase of development to focus on species that lived in those habitats, as that's where the ocean conditions were more predictable on those timescales, which is why we sort of moved into more heavily to work with Hake and also with Dungeness crab. So Hake is being an effort that's led by Mike Malik and Mary Hunsaker, and basically it's going to be relying on the JSCOPE system, this temperature in addition to the undercurrent to try and get at a habitat. Will the hake be more closer to shore, further offshore, which will aid in stock assessment activities, as well as whether or not there will be more in Canadian waters within the JSCOPE domain. Oh, that's wrong direction, sorry. We're also working with the Dungeness crab fishery with state and tribal decision makers to try and bring this forecast system into their decision making. And so for that, we have a couple of different ways that we're working with them. One of them is over the summer in providing forecasts of hypoxia that they can then respond to, and then some decisions around sort of opening. Will the season be opening earlier or later than it has in the past? And that could help inform that decision. So one preliminary result from that ongoing project is that we now have an oxygen map of bottom oxygen that was made with the input of that our advisory council, which includes state and tribal managers. And so what this does is clearly identify observations in the region and landmarks, as well as state boundaries and bathymetry of interest for their management needs. So just the last thing I'll highlight is that there's another seasonal forecast in the works that Mike Jaycox is leading, that it will be California current-wide and relies on the EcoCast model that Elliot Hazen has led. And so this will really, they're looking forward to providing targeted bycatch species forecasts to help inform management actions in the region. And so that is pretty exciting. So I guess just to summarize, I just want to point out that we are definitely in an era, as everyone probably is aware, of rapid ocean change. And these forecasts can help us, see what's on the horizon. We can, ask questions of these short-term forecasts like for Pseudo-nitzschia blooms, should I harvest next week from the seasonal ocean forecast? Kind of will the hake migration reach Canada? Will the crab season be delayed? What is the turtle bycatch risk off California? And then the long-term forecast, which I have not talked about here, but just to allude to, then give us some indication of the global change to the ecosystem. And we certainly are missing some information on the sort of shorter term, like midterm from 1 to 20 years. And but we're working on tailoring these forecasts, for the fisheries councils and other partners as needed. Further skill assessment to understand the limitations of these systems, and then scenarios and ensembles in order to understand the uncertainties and also kind of other outputs that we can provide. So with that, I just want to acknowledge my funding sources and I'm happy to take any questions.